natural photosynthesis, in other words, the green leaf, uses a green dye called chlorophyll to absorb sunlight. And when the light is absorbed, the chlorophyll gets excited and generates electric charges, negative and positive charges. These are then converted in electrochemical reactions in the leaf to oxygen and the sugar, which we eat carbohydrates. The dye-sensitized solar cell also uses a molecular dye, not a p-n junction semiconductor, to harvest sunlight, and it generates electric charges, which then are collected as electricity. I have here an example of a panel that has a red-colored sensitizer. There's another one behind that uses a green dye. It has a similar structure like chlorophyll. And here I show you the photoelectric effect. When I connect the panel, you can see the fan starts turning, wildly turning. Okay. So the electricity is produced not holding directly in sunlight. The cell captures radiation from all angles. That's one of the advantages of the dye-sensitized solar cell. You can see that the dye-sensitized cell, the ones I'm holding, is a very simple device. It has actually two glass plates, and in between we have the active material, which is actually the core of our invention. These films consist of an array of very small nanoparticles that are nanoparticles of titanium dioxide. And these nanoparticles support the dye, so the dye is adsorbed on the surface, and they also conduct the electrons that are generated by the dye to the current collector. And so it's a simple device, and it's easy to produce. The components are low cost, and it's very efficient. The ambient light efficiency is particularly high, and so the direct sunlight conversion efficiency is also very competitive, especially when the panel is held as a glass facade and in vertical positioning. The industrial development has gone on for more than a decade. And so two classes of products have now appeared. One is the panels which we see here. The green panel is industrially produced. This is a panel produced in Korea industrially. And so these are used in facades and balustrades and also as sound walls on the autoroutes. And so we have that one application for glass panels, but there's also an application for the ambient light harvesting devices, where the dye-sensitized solar cell serves to capture ambient light and convert it to electric energy, which then is used to charge devices like an e-reader or an iPhone. And so this application achieves in ambient conditions up to 35% efficiency. Indeed, the great challenge to meet the Paris Agreement is to replace fossil energy by renewable energy. And photovoltaics has to make the major contribution. We have, in the next few decades, we have to increase the capacity of photovoltaic energy generation by a factor of 200. And so the dye-sensitized solar cell, but also the new offspring, which is the perovskite solar cell, that emerge directly from a dye-sensitized cell, they are certainly in a position to provide the additional power we need to meet the Paris Agreement.